Weather is one of the most important concepts for a pilot to understand. We don't want to get ourselves stuck airborne in a thunderstorm or other extreme weather. We need to have a comprehensive understanding of weather information and theory so that we know when to and when not to fly. So we're going to discuss weather forms and how it relates to flying, and then we're going to get into charts and how to interpret these charts and apply them. So we'll start off with the first half of this presentation being about weather theory. And then the second half will be about basically the importance of weather briefings, how to read weather reports and charts in flight weather advisories, and how to make competent go, no go decisions. And why? Because weather has an insanely profound effect on the safety of flight. So, of course, better comprehension of weather theory and weather information services will lead to more competent go, no go decisions. So, let's start off with weather theory. This will be the first half of the presentation. Atmosphere, composition, and stability. There are mainly four gases that make up the vast majority of the atmosphere, that being nitrogen, oxygen, argon, and carbon dioxide. Most of Earth's weather occurs in the troposphere. So this is about sea level to 36,000 feet. Air becomes thinner and temperature decreases with our height, with our altitude, and almost all of our weather occurs here. Then we have our stratosphere. So from the tropopause to about 35 miles above the surface, temperature increases with height due to the absorption of UV radiation. And then there's also the mesosphere, thermosphere, exosphere. I'm not going to get into this too much. We're not even leaving the troposphere in our general aviation aircraft. We're staying well below this. We can't even climb nearly this high. We're staying in the troposphere. Right? Just remember that's important because all of our weather occurs here. Airliners will fly above the troposphere many times, just avoiding any adverse weather and weather altogether. Not us. We're in the thick of it. We're in the soup. When we talk about a standard atmosphere, it's the average conditions throughout the atmosphere for latitude, seasons, and altitudes. So the average atmosphere that we base our performance calculations on is 15 degrees Celsius at the surface at sea level, also 59 degrees Fahrenheit, but we mainly use Celsius in aviation, and 29.92 inches of mercury. So a standard altimeter setting, if we had a perfectly standard atmosphere, would be 2992. Wind is air motion relative to the surface. It affects all phases of flight. There's primary forces that affect wind: pressure gradient force, Coriolis force, and friction. What causes wind? Wind is just caused by the uneven heating of the Earth's surface that causes these pressure changes. And the larger the pressure gradient force, the more wind. So we can look at this pressure gradient force on our charts that we have. So here's an example. Wind will flow from high pressure to low pressure. So in this image here, we have a H for our high pressure system to the right and a low pressure system to the left. Where the pressure difference exists, we have a pressure gradient force that makes the wind blow to equalize the difference. So if I'm flying in the Midwest here, we're going to have strong winds coming from the east because I have this high pressure system wanting to move forcefully into this low pressure in order to equalize. The wind speed is proportional to the pressure gradient force. So these gray lines here are called isobars, and they show elongated areas of constant pressure. So the closer these isobars are, that would indicate to me as someone reading the chart that there is a high pressure gradient force indicating stronger winds. So you can see a weaker pressure gradient force, there's less isobars. The more isobars are closer together, the stronger the gradient, the higher the wind speeds. So it's displayed by the contour gradients, these isobars, these gray lines here. So in summary, closely spaced isobars indicate strong winds. If they're not spaced closely, you're going to get calmer winds. The next is Coriolis force. Coriolis force is basically the way that the Earth is constantly spinning, right, and that will deflect airflow on our planet. So as air is deflected, as our planet spins, air is deflected to the right in the northern hemisphere, and is deflected to the left in the southern hemisphere. It's like if I have a spinning disc right here, and I draw a line in a straight line on a spinning disc, it'll actually be curved. That's what happens in the atmosphere. So you have that turntable illustration right here that really indicates that. The next is friction. Friction between wind and terrain will slow the wind. So the greater the friction and the rougher the terrain and higher speeds. Greater friction with rougher terrain and higher wind speeds. And friction will decrease with height. So of course, if we're farther away from that friction, that airflow is not going to slow down as much. All right, let's talk about wind shear. Wind shear is just a sudden drastic change in wind speed and or direction over a small area. Wind shear can occur at any altitude, and low-level wind shear is commonly what you'll see as a hazard, because if we're low to the ground and we have a drastic change in wind speed and or direction, that'll affect the performance of the aircraft. And it's associated with passing frontal systems, thunderstorms, temperature inversions, and strong upper-level winds. Generally, wind shear is dangerous because it can cause violent updrafts and downdrafts, affecting the performance of the aircraft. And a tailwind that quickly changes to a headwind will increase our airspeed and performance, but a headwind that quickly changes to a tailwind will decrease airspeed and decrease our performance. So just again, around frontal systems, thunderstorms, inversions, and strong upper-level winds, we're going to be extra cautious about wind shear. I got ahead of myself here. I kind of explained this already. Mountain waves. So mountain waves is turbulent air on the downwind side of a mountain caused by stable air. So as air hits the upwind side, it'll create a smooth updraft. So if the wind is coming from the left here, we create a smooth updraft. As it passes the crest, the turbulent air becomes a downdraft, and these downdrafts create these rotors, also called eddies, that can last for miles. And so on the downwind side, the leeward side of a mountain, you'll have all this turbulent air. A lenticular cloud can indicate the presence of mountain waves, and a lenticular cloud looks like kind of like a what do you call that? Like a contact lens shaped cloud that kind of looks like a disc over the top of a mountain. So just because there's no lenticular cloud, that doesn't mean that there's no mountain wave turbulence. But if there is a lenticular cloud, that means there's definitely some mountain wave turbulence. All right, let's talk about temperature. Water is more resistant to temperature changes than land, so air above water will warm and cool slower than air above land. Land will heat up and cool faster than above water. Temperature will decrease about 2 degrees Celsius per 1,000 feet. So if it's 15 degrees Celsius on the ground, at 2,000 feet, it'll be 11 degrees Celsius. But it's not always the case. That's a generalization. If you have something called an isothermal layer, temperature remains constant with altitude. And if we have a temperature inversion, temperature increases with altitude. And remember, we talked about temperature inversion. Right where that temperature inversion lies, we can get wind shear. Remember, temperature inversions can be an indication of wind shear. Moisture and precipitation. So precipitation, it's just water vapor within the atmosphere, and there needs to be sufficient lifting, so condensed water vapor in clouds. And precipitation forms when the water particles in the clouds get too big for the atmosphere, and the atmosphere can't support it, and so that water falls, leading to precipitation. So the growth process is droplets grow large, heavy enough to fall. And that's really it for precipitation. We can also get ice crystals. Water vapor deposits directly into ice crystals. So there's different types of precipitation. We have rain. We have ice pellets, so a shallow layer of freezing air aloft and then deep below freezing layer at the surface can lead to ice pellets. Freezing rain, usually when we have a deep layer of freezing air aloft and then shallow below freezing layer at the surface. So basically that ice, as it falls, cools and becomes a super cooled freezing water. And what freezing rain often does is, as soon as it strikes the aircraft, it'll freeze immediately. And it's one of the largest hazards for structural icing on the aircraft. And snow, below freezing layer from air from top to bottom. All right, well, let's talk about air masses. Air masses are large bodies of air that will take on the characteristics of the environment that it's in. So the source region will dictate what type of air mass it'll be. So classified based on temperature and moisture. So temperature, Arctic, polar, tropical. Moisture, continental, maritime. So I'm in the Seattle area. So oftentimes we get air masses from the Pacific Ocean that then comes on, over the Seattle area. And so we're getting moist, we're getting polar, maritime air masses that affect the Seattle area. So we're getting cold, wet air, and that often leads to rain, which is why Seattle gets a lot of rain. So again, these different types of air masses. So if I said that I had this maritime polar, that's cool, moist air. There's different types depending on the area that you're in. I'm going to kind of gear this to any of my future students that may be watching this video. We have maritime polar air masses that affect the Seattle area. As the air masses move around the Earth too, it can require different attributes. So as the air mass moves over Seattle, moves over the Cascades and kind of gets into the drier eastern Washington, Idaho, then it's going to lose a lot of its water vapor and potentially become hot and dry. So kind of moving from maritime polar to continental, tropical, potentially. Now a front is just the boundary layer between two air masses. Most weather occurs at the border, at the periphery of these air masses at the front. A lot of weather occurs at these fronts, and it's classified by which type of air mass is replacing the other. So we're going to get into the different types of fronts. They're detectable in several ways. Significant temperature gradients, converging winds, decreased pressure as the front approaches, increased pressure after. It depends on the type of front. So let's get into it. The first is a cold front. It's a very steep slopes indicated on our charts by this blue line with blue triangles indicating a cold front. I can look at the blue and I think blue is like cold ice, cold front. It helps me remember it. It's a mass of cold, dense, stable air advancing and replacing warmer air. So this cold front right here is moving forward and advancing. I can almost think about it like a snow plow. That's really advancing through the warmer air ahead. Oftentimes, the unstable warm air gets forced upwards, and this can lead to showers and thunderstorms along the front of, in front of the front. I feel like I could use some better words there, but in front of the cold front. You get what I'm saying. Other weather you can get, in a cold front is, these towering cumulus or cumulonimbus clouds, heavy showery precipitation. You'll get this unstable air because this air is rising. Real quick, stability is the atmosphere's ability to resist vertical motion, and it's usually determined by temperature decreasing rapidly with altitude. So if I have a lot of air moving vertically, the atmosphere is not resisting that vertical development, then that's unstable air. So again, stability is just the atmosphere's ability to resist vertical motion. Anyway, some more weather effects from cold fronts could be lightning, tornadoes, thunder, hail, variable gusty winds, and a drop in pressure and temperature as the front passes. Because, we're going to drop in pressure because we're getting this warm air being replaced by this cold air. Next is our warm front, and it's depicted by this red line with these half circles here. It's a gentle slope as compared to that cold front where it was a steep slope. It's more gentle, and it's when warm air mass comes into contact and flows over a cold air mass and continues to advance. So we can see this warm air mass and this front is moving left to right here, coming into contact with this cold air and then moving over that cold air. So warm air rises gradually. Stable warm air rising leads to widespread stratiform clouds and precipitation ahead of us. So weather we can get is, again, these stratiform clouds, which are just these thick, widespread, super wide clouds that usually cover the entire sky and become this insanely large overcast layer. You can get drizzle, low ceilings, poor visibility, variable winds, and a steady rise in temperature as this front moves. And if I'm right here and the front moves and all of a sudden I get on this side, we're going from cold to warm here. Next is a stationary front. So visually, it looks like half a warm front, half a cold front. A stationary front is when two relatively equal air masses meet and neither one advances. So the slopes can vary, and clouds and precipitation form in the rising air aloft the front. The thing about stationary fronts is the weather associated is that of both a cold front and a warm front, and they can remain stationary over a certain area for elongated period of times, like multiple days. And so you can have terrible weather for many days in a row because of a stationary, being in your area. The last front is an occluded front. And it's depicted by, it's pink right here, but you'll more commonly see it as being purple, and it has the triangle and the half circle. So purple, triangle, and half circle. It occurs when a faster moving cold front overtakes a slower moving cold front. So the cold air undercuts a retreating cooler air mass, further lifting the already rising warm air from the warm front. So this leads to a lot of upward acting force, leading to a lot of unstable air. So the weather we'll get from it is weather from, it's really the worst parts of both a warm and cold front. As the front approaches, expect warm front conditions followed by cold front conditions. And occluded fronts are a huge thunderstorm hazard. Lots of thunderstorms are formed by occluded fronts because there's additional uplifting force pushing this this unstable warm air upward. All right, let's talk about vertical motion and cloud formation. Air cools as it rises. So for the dry adiabatic lapse rate, it's about 3 degrees per 1,000 feet. Lifted condensation level, or LCL, our temp dew point spread is 0, relative humidity 100%, and temperature decreases about 2 degrees per 1,000 feet. As far as cross-country flight planning, we will generally assume that temperature will decrease 2 degrees Celsius per 1,000 feet. As air expands, it'll cool, and vapor will decrease. So water vapor condenses to droplets and ice crystals, and can form clouds. All right. I'm trying to think if there's anything else I want to talk about with clouds. Maybe I'll give a more a better summary on clouds. Clouds will form when the temperature dew point spread equals 0, meaning that our relative humidity is 100%. So if I have I want to get the paint app. So I have a mass of air right here. All right. And so this is my mass of air. And this square indicates how much moisture that this air can take. And on the inside is how much water vapor there is. So maybe it's about half of the square. My relative humidity would be 18%. Or excuse me, it would be about 50%. Now, if I took this same square here, let's say the same square, and I cooled down that air mass. Now, it's the same amount of water vapor in the air, but I cooled the air, meaning colder air can hold less water. And so you can see the point that I'm getting to is if I cool air enough, the air is unable to hold the moisture, so then it reaches a saturation point of 100%, and then water vapor forms, a cloud forms. That's why one reason why relative humidity doesn't really tell you the whole picture of how much water is in the atmosphere, because I can have let's just say this is a high temperature and this is a low temperature. They can both have the same amount of water, but this would be about a 90% humidity and this would be like 50% humidity. They both have the same amount of water vapor in the atmosphere. So relative humidity, again, is relative to the temperature and to the atmosphere that it's in. And so if that temperature dew point spread is 0, and what's my dew point? That's the temperature that air mass needs to be cooled to in order for relative humidity to reach 100%, so that a cloud forms. So let's get more into clouds. There's orographic effects, so mountains and valleys causes air to ascend and descend. I can see as air is forced upwards up this terrain here. As it rises, it cools. As it cools, it can potentially reduce that temperature dew point spread to 0, making the relative humidity reach 100%, causing the formation of clouds. There's also friction effects, so high pressure, surface winds, spiral. This is an important point here. A high pressure system will spin clockwise and outwards, and so winds will diverge away, causing air to sink compress, and warm. So that's why high pressure systems have that sinking air, which is leads to the dissipation of clouds. And so we generally, if we see a high pressure system, we think of it and associate that with better weather. With a low pressure system, it spins counterclockwise and inwards. Winds converge, causing air to rise, expand, and cool. And if it's rising, expanding, and cooling, it could potentially lead to the formation of clouds. And so we associate lower pressure systems with poorer weather and worse weather. There's also frontal lift we talked about in those cold fronts and warm fronts. We've got air that's being forced up a front, in front of a front. As that air cools, it can lead to the creation of clouds. And buoyancy. Air near the ground warms at different rates. So differing air densities allow warm air to rise and cold air to sink. All right, let's talk about cloud forms. There's cirriform, high-level clouds above 20,000 feet composed of ice crystals, and they're thin and white, so kind of wispy, kind of looking on the outside of this presentation right here. They're white and wispy. Nimboform. Nimbo is the Latin word that means rain. So if you hear nimbo and then a cloud, that means it's going to be a rain cloud. There's cumuliform, which is white, fluffy cotton ball looking clouds, and they look really like they're super pretty and you want to fly through them, but a lot of times you're going to get tossed around, and the most dangerous turbulence that you'll encounter is in a big puffy cloud. And stratiform clouds, so Latin for layer or blanket. So featureless low layer that can cover the entire sky and is usually an indication of stable air. Cumuliform clouds are usually an indication of unstable air. So there's different levels of clouds. There's high, middle, and low. We usually operate around the low clouds. Sometimes around middle, not really touching the high clouds all too much. So in the high clouds, there's different types. Cirrus, again, these wispy clouds that are ice crystals. No significant turbulence or icing. There's cirrocumulus, so it almost looks like the clouds got waves, composed of higher supercooled water droplets. You can expect some turbulence and icing if you're up at these high altitudes. And again, this is up, 15,000, 25,000 feet or so. And then cirrostratus, primarily ice crystals, thin, transparent. It can be hard to discern as compared to the cirrus, which you see these wisps. Basically, it's less evident in the cirrostratus clouds. Little, if any, icing and no turbulence. Let's get to middle clouds. Altocumulus. It's the primarily small water droplets resulting in sharp outline and small internal visibility. You can expect some turbulence. A lot of times when you see cumulus clouds, you're going to expect turbulence. When you see stratus, you're not going to expect turbulence. Altocumulus lenticularis, or lenticular clouds. So we'll see this. I'm in the Seattle area, so we'll see this around Mount Rainier. And it looks really cool, but it's an indication of mountain waves, and it can be a strong indication of turbulence, especially if you're flying close to the mountain. Altostratus, sheet of clouds often totally covering the sky, little to no turbulence. And nimbostratus. So we add that word nimbo. Now we're just adding composed of suspended water droplets, and we add rain and snow. No lightning or thunderstorms or hail. Little turbulence, but can pose icing issues if you're above the freezing level. Now the low clouds. This is what we are normally navigating around. Of course, when we're flying visually, we can't fly into the clouds. So we've got our cumulus and towering cumulus. So this is like our thunderstorms. First stage of a thunderstorm as it vertically develops. So this is the first stage of a thunderstorm developing in this photo here. Cumulus, you get some icing and turbulence. You can get some pretty crazy turbulence if you're flying in cumulus, especially in a towering cumulus cloud, which is basically a thunderstorm that's more developed, and there's a lot more vertical development. Stratocumulus, composed of water droplets, soft hail. Virga is just when precipitation is falling, but it doesn't reach the surface. It looks really cool from the air. You can expect some ice and turbulence. Stratus clouds, a lot of times for amazing real IMC when you're flying instrument and you've just got stratus clouds, you've got no turbulence, super smooth air, but just low visibility, low ceilings. Great for instrument flights, not for VFR flights. Precipitation is rare. Icing could still be a hazard, again, if we're above that freezing level, but little to no turbulence. You'll get smooth air in stratus clouds. And then cumulonimbus clouds, exceptionally dense, vertically developed, associated with heavy precipitation, lightning, and entire spectrum of flying hazards. So you're going to run into some crazy turbulence, some crazy icing potentially. Don't fly anywhere near a cumulonimbus cloud. All right, turbulence results from convective currents and rising, sinking air. If we have an unstable atmosphere, we'll run into turbulence. If we have a stable atmosphere, we'll run into less turbulence. Cumuliform clouds are convective turbulence signposts. That's like warning, warning, there's turbulence. Expect turbulence in and beneath the clouds. No indication in dry air. So just because there's no cumuliform clouds doesn't mean there's no turbulence. But if there is, then you know there is. There's also mechanical turbulence, so caused by obstructions. Wind that's having to blow around trees, buildings, and mountains on the leeward side will create this mechanical turbulence. And mountain waves, like we talked about, turbulent air on the downward side of the mountain. And again, wind shear. Wind shear is, again, a rapid change in wind speed and or direction that causes turbulence. Temperature inversions can... You'll run into turbulence where there's a temperature inversion, and you can actually run into clear air turbulence, but this is run into by the airline guys at high altitudes, particularly between the core of a jet stream and the surrounding air. If you start to slip outside that jet stream, then you're going to run into strong clear air turbulence. All right, let's talk about thunderstorms. Thunderstorms are an extreme hazard. And there's three main ingredients for a thunderstorm to form. You need basically unstable air, you need sufficient water vapor, and you need rising air or a lifting mechanism. There are three stages of a thunderstorm. So there's three ingredients for a thunderstorm to form, and all are required. If one is missing, you don't get a thunderstorm. All three are required. The three stages of a thunderstorm is first the towering cumulus stage. So we have this towering cumulus stage where it's primarily characterized by these strong updrafts, where we have these updrafts that push warm, moist air upwards until the moisture becomes too heavy for the clouds. Then we run into the mature stage. When precipitation reaches the surface, that marks the beginning of the mature stage. The precipitation can also drag the adjacent air downwards, creating strong, cool downdrafts. So we're going to have, during the mature stage, it's characterized by having one, precipitation, but also strong updrafts and strong downdrafts. And those updrafts are really what's feeding that thunderstorm to continue. The last stage is the dissipating stage. It's characterized mostly by downdrafts that replace the updrafts. This cuts off that moisture provided by the updraft, so basically it's losing its supply, it's losing its feed, and so it gets replaced by these downdrafts until the precipitation eventually tapers off and the thunderstorm ends. One thing to note, the anvil cloud top will indicate the end of the mature stage of a thunderstorm. Always expect lightning in a thunderstorm and avoid thunderstorms by at least 20 miles. Don't fly anywhere near a thunderstorm. There's different types of thunderstorms. Three main types. So we have three ingredients, three stages, and then now three types of thunderstorms. First is the single cell. It's rare, easily circumnavigated, unless you're flying at night or you're embedded in the clouds. But if you see it during the day, it's easily circumnavigated. Then there's the multi-cell. One thing to say about the single cell is it lasts roughly for 30 minutes before it dissipates. The multi-cell, it's a cluster of cells at various stages in their life cycle. So the first cell matures and then gets carried downwind, and then a new cell forms upwind and matures and carries downwind. And so it goes on for a long time and can last for several hours or even longer. Lines of thunderstorms can extend for hundreds of miles and persist for hours. The last is a supercell. It's a single quasi-steady rotating updraft persisting for an extended period of time. It can also be a part of a multi-cell thunderstorm, and you can get, it's extremely dangerous. You can get things like 9,000 foot per minute updrafts. Even if there's a single cell thunderstorm in my area, it only lasts for 30 minutes. I'm going to wait. Most of the time, you'll have multi-cell thunderstorms. Just don't fly anytime you're in thunderstorms. Some hazards with them are lightning, adverse winds, downbursts, microbursts, we'll talk about that, turbulence, icing, hail, altimeter changes, static electricity, and tornadoes. So, one of the hazards we saw of a thunderstorm is a microburst. What's a microburst? It's a small-scale, intense downdraft that reaches the surface and then spreads outwards in all directions. They're hard to detect. They usually last anywhere from 5 to 15 minutes, usually not a lot longer than 15 minutes. And they're found where there's convective activity. They're found where there's thunderstorms. That's why we're avoiding these thunderstorms by at least 20 miles. We don't want to run into any microbursts. Usually 1 to 2 miles in diameter, 1,000 feet depth. Downdrafts of up to 6,000 feet per minute. And so if I'm flying along at 3,000 feet and I run into a 6,000 foot per minute descent, then I've got 30 seconds till we're smashing into the ground. You can see how this is a hazard. Headwind losses of 30 to 90 knots. That can stall the aircraft very easily. And very strong turbulence and hazardous changes in wind. So if I'm flying through a microburst, if I'm on this backward side of it, I'm going to get an increased headwind, and I'll actually get increased performance. But as I get to the center, then I'm going to be in the center of the downdraft. Remember, up to 6,000 foot per minute downdrafts. And then as I increase in my tailwind, I'm going to rapidly lose performance. Anytime I enter a microburst, just climb for at your VY airspeed and then hold it there, because you don't want to be smashed into the surface, especially when we're operating a general aviation aircraft relatively close to the ground. Some more about microbursts. Visual conditions of a microburst is convective activity. They're hard to detect. You can see a ring of blowing dust, intense rain, but virga at the cloud base. There's not a lot of visual indications of microbursts. Many airports have LLWAS, which is low-level wind shear alert system. Small airports may not have that. To avoid it, don't fly in thunderstorms. Be alert for visual cues, and if we have this low-level wind shear alert system, we'll utilize it. If not, we can look at things like PIREPs, which are a pilot-given report, which we're going to talk that further into the presentation when we talk about interpreting weather data. All right, frost and icing. Frost forms when dew would form, but in freezing temperatures. So dew would form if the surface of the aircraft causes the surrounding air to cool beneath its dew point, and if that dew point is potentially in the freezing temperatures, then it becomes frost on the wing or frost on our aircraft. This poses a hazard to our aircraft. It'll disrupt the smooth airflow over the wing, drastically reducing lift and increasing drag, potentially increasing weight, but that's not as much of the hazard as the reduction in lift and increase in drag. So we should clean the aircraft thoroughly. It's actually illegal to take off if we have any frost on our wings. So we have to make sure we clear all the frost in order to make sure that we have enough performance. And then icing. Also, we're not allowed to take off with icing on our aircraft. There are 3 main types of icing. But first, for structural icing, for us to encounter that in flight, we have to be in temps around freezing or close enough to the surface of the airplane, structural icing to form. Temperature needs to be around freezing or close enough for the surface of the plane to be freezing. And we have to fly through visible moisture. So if we're in freezing temps and we're flying through visible moisture, that being a cloud, for example, or fog, same thing. You know, if fog is just a cloud on the ground, then we're going to run into icing. So what are the different types of icing? We've got rime. Small supercooled water droplets freeze as they strike the aircraft, giving a rough, milky, opaque look because there's tiny little pockets of air inside those supercooled small water droplets as they strike the aircraft. What else do I want to say? Again, it has the appearance of rough, milky, beady looking ice in jagged form. Clear ice is the dangerous one. Heavy, transparent, smooth ice that forms when large water droplets strike the aircraft and spread along the surface and then freeze. It's more hazardous. It's clear, so it's harder to detect. It drastically changes the shape of the wing, reducing lift, increasing drag, and adds weight. So that's the trifecta of terrible performance. And what we'll run into most of the time is mixed ice, just a mixture of both of them. So icing can degrade our engine performance, destroys the airflow over the wing, reducing lift. Ice as thick as sandpaper reduces lift by 30% and drag by 40%. Large amounts of ice can reduce lift, increase drag by 80% or more. That is so dangerous. We don't have any sort of de-icing equipment on our aircraft, so we just cannot get ourselves into a situation where icing would form. And that comes into understanding when does icing form and looking at our charts and making that decision on the ground as to will we pick up icing on this flight? If so, do we have an exit strategy? Do we want to take that risk? And if we don't, great, we stay on the ground. Clear icing, more hazardous than rime icing. The freezing level is very important because if we're flying in temperatures that's below freezing, into visible moisture, we will pick up structural icing. Now, below 15 degrees Celsius, most water vapor becomes ice crystals. Between 0 and negative 15 degrees Celsius, supercooled water droplets make clear icing very rapid. Higher and colder temperatures tend to produce more rime or mixed icing. All right, fog. Fog is just a cloud on the ground. And it's characterized by our visibility being 5/8 statute miles or less is what fog is. It's just a cloud at the surface. There's some different types of fog. There's radiation fog. So we have terrestrial radiation that cools the ground, and the ground cools the air, and fog forms. So on clear, calm nights with little to no wind, when the ground cools, it cools the air above it, cooling that air to its dew point, causing the air to saturate, causing there to be fog. So comment on clear, calm, cool nights. We also have mountain and valley fog. So the ground cools overnight. Dense cool air mountain sinks into the valleys, cooling that air in the valley. The cooler air lowers the temperature towards the dew point. Once that spread becomes 0, fog forms. Next we have advection fog. This is when moist air moves over a colder surface, then cooling that air beneath its dew point. It's common along coastal areas. We have wind that pushes warm, moist air over a colder surface. That colder surface cools that air to its dew point, causing the air to saturate, creating that fog, and it deepens with winds up to 15 knots. Stronger winds will tend to lift the fog, so wind between about 5 to 15 knots is perfect for the conditions that would make advection fog be created. Next, we have upslope fog. If we have terrain that airflow is forced upwards, we know air gets cooled as it gets higher up in altitude. So it's forced upsloping terrain, cooling it to its dew point, creating fog. Again, winds of 5 to 15 knots are most favorable for upslope fog. We also have frontal fog. When air flow is lifted, because we've got a front right here, this warm, moist air is lifted over this colder air, leading to the creation of clouds and potentially precipitation. If the cold air below is near its dew point, the evaporation may saturate and cold air and can form fog. So that's where we have this fog right in this cold air here, because it's being cooled even more down to its dew point, potentially creating that fog. More common with warm fronts than with cold fronts, and this fog can be very dense and continue for an extended period of time, especially with a warm front that moves a lot slower than a cold front does. We also have steam fog. It's when very cold air moves over relatively warm water. As the warm water, the moisture evaporates, it'll create this look of like steam coming off from the water. So the difference now between fog and mist, because they're kind of the same thing, the only difference is the degree to which our visibility is obstructed. So anything greater than 5/8 statute miles up to 7 statute miles will be considered mist. Next is haze. Haze is the suspension of small air particles, giving the air an opalescent appearance. Opalescent just means showing varying colors because it can reflect light. Occurs usually in stable air. The visibility will vary depending on if you're facing toward or away from the sun. The main hazard is reduced visibility, but haze doesn't usually reduce visibility too much, and it occurs in stable air. Smoke can reduce our visibility. Suspension of small particles produced by fire can reduce visibility to 0, and it's toxic. Smoke it's slow to dissipate, it's toxic, it reduces our visibility, and that makes it a hazard. Volcanic ash is we have these fine rock powder that reduces our visibility. It can also cause damage to the aircraft, not just the airframe, but if it gets sucked into the engine, it can damage the engine. Others is blowing snow. Snow lifted to a height of 6 feet or more, reducing visibility to less than 7 statute miles. I've never had an issue with blowing snow. I'm just going to kind of skip through this one right here. And sandstorms. I'm in Seattle. I'm not dealing with sandstorms, but particles of sand carried aloft by strong winds. It's kind of like a dust storm, more localized. And sandstorm usually between 10 and 50 feet above the ground level. So getting a weather briefing, that's pretty much the main points for weather theory, and we'll kind of transition towards weather information. The importance of a weather briefing is extremely important. First, 91-103 states that the PIC shall become familiar with weather reports and forecasts, and everything, all information regarding the safety of that flight. This will help us to be expecting, or know what to expect with the weather and make an informed go, no-go decision. There's a lot of different weather sources out there. You've got different things like weather apps and the internet, the Weather Channel, whatever. What we need to do is have a comprehensive weather briefing that's approved by the FAA. So we can call Flight Service Station by going to 1-800-WX-BRIEF. There's also a website. Most common that we'll do is use aviationweather.gov. It's set up by the FAA, gives us the raw source information, and we're going to go on aviationweather.gov to get our weather and scroll through. Additionally, you can use ForeFlight to get your brief. It gets from the same information as aviation weather. And you can do a self-brief. But all my students, we're going to use either 1-800-WX-BRIEF. That's not as common. I've only done it a couple times, but it gets the job done. Aviationweather.gov the vast majority of the time. And if you have ForeFlight, great. It'll tell you everything. You can even put your route, send that to flights in the ForeFlight app, and then it gives you an entire weather briefing. In flight, you can talk to Flight Service Station, so you can do it as published, or the universal frequency is 122.2 in the Seattle area, 122.5 for the Seattle radio. You can use ForeFlight, and if we have FSB, I've got a Sentry or avionics that allow you to use FSB or satellite weather. Amazing. Okay, let's talk about METAR. A METAR is an airport routine hourly weather observation. It's updated hourly. If something changes and it needs to be updated again, you can get a special METAR. So that can happen anytime. But if it's just a routine METAR, it'll happen every hour. So this is a METAR. When you get the METAR, it looks just like this on the top, except not going to be color coded. So let's break down the METAR. First is the type. Is it routine or special? If it says Speci METAR, then it's a special, usually indicating a drastic change in weather. 99.999% of the time, you're just going to see METAR. You're going to see the station, so your home airport, and then the date and time. The first two digits are the date, so 16th day past the month, and the last four digits are the time in UTC. Most METARs I've seen are done 53 minutes past the hour, and that's when they're updated. Modifier, sometimes it'll be another thing that's a automated weather source, or if you're at a towered airport, usually it's done by the controllers. Next is our wind. So the first three digits are for the wind direction. So the wind's coming from 140 on a compass, and at 21 knots. The G, in the case of gusting winds, shows peak gusts. So winds coming from 140 at 21 knots, gusting to 26 knots. Next is our visibility in statute miles. So we've got 3/4 statute miles visibility. Super low visibility on this METAR. Next is any other weather indicator. So qualifiers showing intensity, proximity, descriptors. So negative sign is light, plus sign is heavy, VC is in the vicinity, SH is showers, TS is thunderstorm. I think FZ is freezing. Then we can also see DZ is drizzle, RA is rain, HZ is haze, sandstorm, dust storm, snow, etc. So what we have here is light rain. And then we've got BR. BR means mist. You can kind of think about it by just thinking about it as it being baby rain, mist. BR, baby rain, mist. That's the way I memorized that. Next is our sky condition. So the amount, height, and type. So if we have clear skies, scattered clouds, broken layer, overcast layer, and it's given in 3 digits in hundreds of feet. So we have a broken layer at 800 feet, so you kind of just add 2 zeros after whatever number it is here, and an overcast layer at 1,200 feet. There's our sky condition. Temperature dew point. Temperature is 18 degrees, dew point is 17 degrees. So if this air cools down 1 more degree, then we're probably going to get fog. And this low dew point spread is probably the reason why visibility is so low and why the clouds are so low. The larger the dew point spread, generally, the better the visibility and the higher the ceilings. Next is our altimeter setting, which we'll put in our altimeter. It's 4 digits preceded by A. So altimeter setting is 29070. And then there's any remarks, such as wind data, variable visibility, pressure info. So if I was reading this METAR, I'd look at it. Okay, 16th day past the month, 1753 Zulu. Winds 140 at 21, gusting 26 knots. 3/4 statute miles of visibility, light rain and mist. Broken layer at 800 feet, overcast at 1,200 feet. Temperature 18, dew point 17, altimeter 29070. And a lot of times, past the remarks, you'll get things, again, like wind data, variable visibility, pressure info. You can also get things like more precise temperature dew point spread. It'll give you like 18.4 and 17.8, for example, or whatever it may be. All right, the METAR reports winds in the true degrees. If I'm looking at a chart, 00000 would mean calm winds. Winds greater than 100 knots are preceded by a P. And sky conditions. So the amount of sky coverage is reported in 1/8 inch of the sky. So if clear skies, less than 1/8 of our sky is covered by clouds. So that will be sky clear, clear skies, few clouds. That will be what it'll say on our METAR. Few clouds are 1/8 to 2/8 obstruction. Few clouds scattered 3/8 to 4/8. Broken is 5/8 to 7/8. So this is where technically when we talk about a ceiling is a broken layer or an overcast layer. An overcast, the whole sky is covered up. The next is a TAF, or a terminal aerodrome forecast. Weather outlook within 5 miles around an airport. It's an airport weather forecast for specific time periods. It's issued 4 times daily, valid for either 24 hours or 30 hours. Depends on the airport. Some airports have TAFs that are valid for 30 hours. Same descriptors and abbreviations as a METAR. So for a METAR, we'll have the type. So this is an example of a TAF. So we have the type, TAF, or if it's amended, TAF amended. The station, so here's the station of whatever airport this is at. Date and time, first 2 digits are the date, number of days passed in the month, and then the time in UTC time. The valid period. So then we have the valid period. So the first 2 digits are the date, next 2 are the start time, and the last 2 are the end time. So first 2 digits are the 11th. Excuse me. Second 2 is the start time, 12 Zulu, and then the last 2 is the end time at 12 Zulu the next day. So this is a 24-hour TAF. And then we have our wind, 150 at 12 knots. Visibility is a little different. It shows in statute miles, but on a METAR, it'll show if it's 10 or greater, it'll just say 10. If on a TAF, it just shows 6 or greater. So P just means greater than 6 statute miles visibility. Then we've got our weather, same as a METAR. Sky condition, so for us, broken, 9,000 feet. Then we've got the change group. So from a certain time, then this is the weather. Becoming, there's a gradual change. Temporarily, it's temporarily this weather, or a probability of thunderstorms and precipitation. So from temporarily. Um, 12:14 Zulu, 5 statute miles visibility, baby rain, that's missed. From 15 Zulu, wind 160 at 15, gusting 25 knots, greater than 6 statute miles visibility. Broken at 8,000 feet, overcast at 15,000 feet, probability of 40% at 0004 Zulu for 3 statute miles, thunderstorm with rain, broken cloud at 3,000 feet, cumulonimbus. So at this time, we're looking at some thunderstorm activity. Then from 4 Zulu, wind 140 at 8 knots, greater than 6 statute miles visibility, scattered 4,000, overcast 8,000. Looks like the weather's clearing up here. Then it again gets worse at 4:08 Zulu, 3 statute miles, thunderstorm rain, overcast 3,000, cumulonimbus, and becoming at 0810 Zulu, 320 at 7 knots. So that's how we look at a TAF. Eventually, you look at these METARs and TAFs, and it's easier than reading it in plain English. All right, next is our graphical forecast GFA tool. It's a set of web displays to give a complete picture of weather that may affect a flight. Forecast for en route phase of flight, locations, especially if they don't have a TAF. Now let's pull up aviation weather. So maybe I can start with a METAR, like we talked about before. So here's the METAR at the Renton Municipal Airport. It says Renton, 15th day past the month, at 20:53 Zulu. Wind is 0000, so we've got calm wind, 10 statute miles visibility. Overcast at 6,500 feet. Temperature is 06. Altimeter is 03. Altimeter 3026. Remark, AO2 means that there's a precipitation discriminator at the airport, so it can tell if there's snow versus ice pellets versus rain. If it says AO1, it can't tell. Then it gives us sea level pressure, and then gives us a more accurate temperature dew point spread. So positive 6.1 degrees temperature, and then our dew point looks like positive 3.3 degrees. So there's a METAR. A TAF, like the Boeing field TAF here. So 1520 Zulu. Winds are calm, 10 statute mile. Oh, that's the METAR. I'm going to start with the TAF. So 15th day past the hour, 1735 Zulu. Valid from the 15th to the 16th at 18 Zulu. Wind 170 at 5 knots, greater than 6 statute miles visibility. Overcast at 5,000 feet. Then from on the 15th at 20 Zulu. Wind 130 at 6 knots, greater than 6 statute miles visibility. Looks like minus RA, which means light rain. Scattered layer at 3,000 feet, overcast layer at 4,500. The next one being at the 16th at 6 Zulu. Wind is 160 at 6 knots. Greater than 6 statute miles visibility. Again, light rain. Scattered 15, broken 2,200 feet. Overcast 3,500 feet. So this is how we read a METAR. So a lot of light rain, not uncharacteristic of Seattle to be like this. Now let's go to the GFA tool, because we were just talking about that. So this is our GFA tool. GFA forecast is all these different things. So if I want to know the ceiling and visibility of my area for a specific time, maybe I'm flying at 4 Zulu, and it'll be going on during this time, then I can look at that. These blue areas, I can look at the legend to let me know, oh, that's areas of minimum VFR. And so I can even draw my route as well. If I was going from I don't know, let's say the airport I'm currently flying out of now to, I don't know, to an airport that's kind of nearby. So I can look right here. I can even change the options to give me, instead of flight category, I can get my ceiling. So it looks like the ceiling here is staying above 2,000 feet. If I thought visibility might be a concern, it'll tell me if visibility gets below 5 through the different color. And again, I'm just clicking the legend on the bottom right to give me more information. So if I was making this flight maybe at about this time at my destination, looks like visibility drops to about 3 statute miles. That would definitely be a consideration for the flight, especially since I could be potentially wanting to fly visually, and I have this dropping visibility that could help me make a decision to say, no, I don't want to fly today. Also, these 2 dots means light rain. 3 dots just means rain. So again, not uncharacteristic of Seattle to see all this rain. These GFA tool, it gives us a lot of things, again, like clouds. So I can see the cloud coverage at different times. And again, this is all calculated. This isn't guaranteed to be what the cloud coverage is going to be. But if I was flying during this time, overcast at 11,000 feet, overcast 9,000 feet. So I'm going to have plenty of cloud coverage here. If I want to look at precipitation, here we go. Chance of rain, snow, ice, what have you. And I'd definitely be getting, likely be getting rain, especially the further west I go here at this specific time. Then I can move on to thunderstorms. If I do run into thunderstorm, looks like there's winter storm warning. But this is over the mountains, over the Cascade Mountains to the east. Let me see if I can find a storm. Here we go. So we've got some nastiness happening in like Louisiana. And this is the symbol where you'll see for thunderstorm. It's kind of like this box with this squiggly line and then the dot on top. So again, all this is available in this GFA tool. It's an amazing resource. Again, check the temperature. I can check winds, turbulence. So it looks like even in this whole area, there's a low-level wind shear alert right here. Airspeed loss or gain of 20 knots or more beneath 2,000 feet. That would be a great consideration for this flight. These darker areas are showing areas where there's, moderate to severe, stronger turbulence. That makes sense. The Olympic mountain range is right here. So when we talked about our mountain wave turbulence, as that air causes friction and then is spinning around the mountains, it's going to create more turbulence. So that makes sense. Things like icing too, we can go ahead and check out. And it'll give us things like icing severity, trace, light, moderate, heavy. SLD, I'm not sure what SLD is. It's SLD icing. Let's find that out together. Super cool. Okay, super cool large water droplets. That's what it is. That is an extreme hazard because that's the fastest way to pick up icing when you're flying. So that's the GFA tool. You use it for so many different things. It gives you web-based illustrations, and it's very useful because if I'm flying to an airport without a TAF, even the home airport that I'm flying out of right now, it doesn't have a METAR. This GFA is a super useful tool. So our GFA tool, weather reports and charts. They updated the way it looks on the website, so we went through and we saw, ceiling, visibility, thunderstorm, icing, turbulence, winds. It looks a lot better now. Also, we have model output statistics, or MOS. In ForeFlight, we can see MOS weather forecasts. It's a statistical method for looking at historical observations and statistically trying to predict what the future is going to do. It's completely automated, and it gives you potentially better aviation weather planning. However, it's not a legal weather source. Its forecasting absolutely sucks. It's wrong all the time. Even METARs are wrong sometimes. This thing is wrong all the time. The MOS, I feel like, constantly saying it's going to be VFR. Get to the airport the next day, and it's totally IFR. It's wrong all the time. No precipitation discrimination. It's only available in the U.S. So use it potentially as a supplement, but don't rely on it at all. It's wrong constantly. Next is our surface analysis chart. Analysis of the lower 48 states gives us the high-low pressure system, fronts, temperatures, wind direction, speeds. It's digitally created by a computer every 3 hours, and surface weather observations. So if I go to our products and I go to prog charts, this is the same thing as our surface analysis chart. So you can see here, we were looking before at different fronts and high and low pressure systems. So H is a high pressure system, low is a low pressure system. Looks like we've got a cold front right here, warm front. Look at that. Remember I was talking about occluded fronts? Purple. And we also have these gray lines here. These gray lines are isobars, indicating strong or weak pressure gradients. So the closer that these lines are together, the stronger the pressure gradient, meaning the stronger the winds. So in Seattle right now, we've got this low pressure system off the coast, and we've had this high pressure system out here. And so we've had a lot of east to west winds. It actually makes for some good crosswind practice because all these runways are north-south. So had some good crosswind days here, some good practice. Anyway, that's our surface analysis chart, also known as our prog charts. This is just the legend for what can show up on it: cold, warm, stationary, occluded. If we see these gaps, it's either it's this frontogenesis or I want to say this right, frontalysis. So that's as a cold front is forming, or as a warm front is forming, or as it's dissipating. You'll see those gaps. A trough is an elongated area of low pressure. You'll see it by these. It'll be orange line. High-low pressure system. If there's a tropical storm or a hurricane, you'll see this. You'll also see, like when we look at, where can I go to get a good look at this? Like on our GFA tool, I think it was have observations. Here we go. So kind of above like these airports, we've got these numbers on the outside like this, right? And so how we read that is we've got the wind. So kind of think a bit about this as where the wind is coming from. The number on the top left is temperature, then the weather. So 4 dots right here just means rain. So temperature, dew point underneath the weather. Sea level pressure, pressure trend. So kind of just looking for a minus or not, if that's trending, pressure's trending down or up. And then sky cover will be indicated by how much is filled in at this circle. So you can kind of quickly be able to look at this and be like, it's completely filled in because there's an overcast layer at 6,500 feet. And that ceiling will be on the right side. So we have the temperature, dew point, visibility, 2.5. That would mean our sea level pressure, and the height of our ceiling, 6,500 feet and 6,000 feet for Boeing Field here. Also, that little like wind bar, each of these pegs is 10 knots, half is 5. A solid filled in one is 50. So that'll tell you the wind direction and speed. Calm wind, it'll just be 2 circles. So I can see wind blowing from the south, so I've got wind blowing up from here at 5 knots. wind coming out of the northeast at 25 knots, calm wind. And here, I've got wind blowing from the west at 50, 60, 70, 75 knots. So we saw this before for rain, 2 dots, light rain, rain, heavy rain. Same thing for snow, looks similar. So for thunder, like we saw when we were looking at Louisiana, we've got this thunder with rain, this thunder with snow, thunder with no precipitation. There's no dot. We gotta think of the dot just as being rain and precipitation. Shower for rain and snow, drizzle, freezing rain, ice pellets, fog, haze. Make sure to having these icons memorized. It's pretty simple. And then sky cover. Clear, scattered is half, partially cloudy, mostly cloudy, overcast, sky is obscured, and sky cover missing. So if maybe the station isn't reporting sky cover and they're doing maintenance on that station, you could potentially get that M. And then pressure plotted in tenths of millibars if it's falling or rising, and the pressure trend. Don't need to fall into this one too much. This is our surface analysis chart. A lot of times has radar on top. Again, radar is showing where precipitation is. Basically, a radar signal is sent out, and as it hits precipitation, it gets reflected and gets sent back to the station. And so we can see where there are areas of precipitation and areas where there's a lot more moisture being developed are occurring. Or you can do satellite composite, showing you your clouds and your rain again. When we were looking at our GFA tool, that included our ceiling and visibility. So it's great for looking at large picture, especially if you're doing a long cross country, as to what kind of ceiling and visibility you're going to be running into. Next is our winds and temperatures aloft forecast. So these are perfect for when we're getting what we're using for when we're planning a cross-country flight plan. Wind and temperatures are based on altitude for specific locations. They're published twice a day. I hope this link works. Some of the links are a little outdated. If not, let's get winds. If I can back up here. Products. Here we go, winds, temps data. That's what I'm looking for. So I'll go to the northwest where I'm at. West Pacific. Will that get it for me? No, I think Pacific Coast. There we go. So I'm in Seattle. So this I'm looking at here. So I've got like Tacoma, Portland, San Francisco, Yakima. This is what I'm going to use. And so for each 3,000 feet, it gives me what the winds are. So this is really helpful for when we're doing, cross-country flight planning. So how do we start? So the first 2 digits here are the direction. So at 3,000 feet, winds coming from 190 at 24 knots. At 6,000 feet, this is where we'll get our first wind, direction, and speed plus our our temperature. So wind from 230 at 25 knots, temperature -4. 9,000, 240 at 30 knots, temperature -5. So temperature is going up pretty slowly, so indicating probably more stable air here. Let me find a hard one where it doesn't have that minus sign anymore. Negative temps above 24,000 feet just because it's implied. So at 30,000 feet above Seattle, wind from 260 at 32 knots, negative 47 degrees. There's not a tough one here. I'm going to find just a different one. Here we go. So now I've got, what is this? Wind from 720 at 44 knots minus 44 degrees. That doesn't make sense. So if I see a 7, or an 8, or a number that doesn't make sense, I'll subtract 5. So I'm going to subtract 5 and say wind is minus 5, 220, and I can almost add a 1 right here. So wind 220 at 144 knots, temperature above 24,000 feet is negative, so minus 44 degrees. Wind 220 at 144 knots, minus 44 degrees. Anytime the wind is greater than 100 knots, they'll add 5 to the first number here, and this will just be the tenths and or the hundredths and tenths number here. Okay, make sure I'm back on the slideshow here. Did I talk about that? Talked about wind. Cool. Next is our convective outlook chart. It'll depict where an area's forecasts have severe and non-severe convection. So that being tornado, thunderstorms. We were looking before at thunderstorms in this area. So if I bet you if we looked at our convective outlook chart right now, we would see the thunderstorm area in that area. So if I looked at our convective outlook chart, which is, I guess that's literally just now incorporated into the GFA tool. I wonder if they have the old one. Just out of curiosity, I'm going to see if they have the old one still in here. The convective outlook. Do they? No. Convective. Here we go. Convective forecast. So I guess we can see it in this area. It looks a little different. But anyway, you can just use the thunderstorm tab here in the GFA tool. And again, we can kind of look back in Louisiana. Boom! Nasty over here. Big nasty stuff going on over here. But anyway, on the old aviation weather website, this is what it looked like. Looks a little different for us now. Looks a lot better for us now, actually. TSTM, less than 10% chance, marginal, a little higher, slight, a little higher, and then gets even higher. I'm going to skip over that because the chart is different for us now. Now we have in-flight weather advisories. I don't know why it's saying that. Just think about it as weather advisory service. We have AirMets, SIGMETs, convective SIGMETs, and PIREPs. AirMets stands for Airman Meteorological Information. So it'll detail weather data that's of interest to all aircraft, yet potentially dangerous for aircraft that are smaller with limited capabilities, like us. There's 3 types. But first, they're also issued every 6 hours with intermediate updates as needed. AirMets, there's AirMet Sierra, Tango, and Zulu. Tango, think T for turbulence. So turbulence, strong winds, low-level wind shear, we'll get a Tango Sierra. And the type of turbulence it'll be reported is at least moderate turbulence. Next, Sierra. So think of IFR, mountain obscurement, Sierra, I can't see, era. There you go. Think about it like that way. And then Zulu for like freezing. That's how I memorize it. So icing and freezing levels are indicated in these types of AirMets. If I go to here we go, AirMet. So here's some AirMets here. Here's a blue one. So this is a Zulu AirMet for icing. So icing from the surface up to 12,000 feet, moderate. Here's a Sierra. Because of mountain obscuration, I can't see anything. And then here's a Tango, because it's turbulence and sustained winds greater than 30 knots. Moderate turbulence, low of wind shear. Things that involve turbulence is a Tango. So 3 types of AirMets. Sierra, Tango, Zulu. Next is SIGMETs. Stands for, a SIGMET is for significant meteorological information. It advises weather data that's potentially dangerous to all aircraft. Remember, AirMet was weather data that's of interest to all aircraft, yet only potentially dangerous for aircraft with limited capabilities generally. It can, of course, AirMet information can pose a hazard to larger aircraft, but it's especially dangerous for smaller aircraft with limited capabilities. A SIGMET means it's weather data potentially dangerous to all aircraft. In-flight non-convective weather, so weather that's not has to do anything not associated with thunderstorms. So issued for severe icing, extreme turbulence, clear air turbulence, dust or sandstorms that reduce visibility to less than 3 miles, and volcanic ash. They are valid for 4 hours unless it's a hurricane-related SIGMET, and it's valid for 6 hours. So if we go back to aviation weather, I go to, products, and I go to SIGMET. I'm sure there's going to be one somewhere here. Here we go. We've got one right here. I'll use this one. So remember, it's for severe and extreme icing or turbulence or widespread dust sandstorms, reducing visibility to 3 miles or less, or volcanic ash. So this one is over Vancouver from 0 to 3,000 feet, and they've got severe turbulence being reported over here. Very dangerous. Not going to be flying in any sort of SIGMET, especially if it's reporting severe turbulence near the ground. Now there's a second type of SIGMET. There's a convective SIGMET. So this, same thing, keyword difference from the SIGMET is the word convective. So it alarms more extreme weather associated with thunderstorms. Issued 55 minutes past the hour. It's updated as necessary. They're valid for 2 hours. So it includes things for like severe thunderstorms with surface winds greater than 50 knots, hail at the surface 3/4 inch or greater in diameter, and tornadoes. Also, you can see them for embedded thunderstorms, line of thunderstorms, or thunderstorms with heavier, greater precipitation affecting an area of at least 40% of an area greater than 3,000 square miles. So let's find ourselves a convective SIGMET on aviation weather. And we knew all the nastiness that's going on over here. And again, I'm on just the SIGMET page. And this has con for convective SIGMET. Convective SIGMET, we've got area thunderstorm moving from 230 at 50 knots, tops at 44,000 feet. Huge thunderstorm going on over here. So I'm glad we had this as an example today. All right, let's go back to the presentation. Next is Center Weather Advisory. It's an unscheduled in-flight weather advisory issued for hazardous weather. So unscheduled if, produce weather beginning in the next 2 hours. Maybe there's weather that doesn't meet the criteria of a SIGMET or convective SIGMET, but it's still, or AirMet, but it's still adversely is affecting safety. It could be a center weather advisory. I don't know that I've actually ever seen, let's see, here we go. We've got a couple here. Looks like this one's for icing from 13 to 14,000 feet. Turbulence. Where is this one at? From 20 miles northeast. Severe turbulence. Oh, wait. Area of moderately occasional severe turbulence from 33,000 feet to 34,000 feet reported by aircraft. Gotcha. Well, there you go. And this is center weather advisory here. So may not meet the conditions for an AirMet, a SIGMET, or convective SIGMET, but it could still adverse safety, and so everything else is thrown into the center weather advisory. So it's kind of like a nowcast for conditions developing within the next 2 hours, and it's valid for 2 hours. Next is a PIRAP. Now we talked about using a PIRAP for to look at PIREPs to avoid wind shear. A PIREP is just a pilot-generated weather report. So it allows for real-time weather reports like cloud tops, icing, turbulence, cloud bases. Helps fill in the gaps between reporting stations. So we can look at PIREPs. Where are PIREP data? I don't want to. I want to look at it on a map. What's nice is on my iPad and like in ForeFlight. Here we go. Observations. Maybe it's in here. I want to get. Okay, pirates are enabled. Here we go. So each of these icons, like here and here. Let me clear this just to make it easier. So like these icons here are PIREP. So if I click on this one, a pilot was reporting that over Hoquiam, time 21:54 Zulu at 33,000 feet. They're in a 737. They're experiencing moderate turbulence 18 minutes ago. What about this person? Over wherever that is at 37,000 feet. They're in, I think that's that 777. They're experiencing moderate chop 44 minutes ago. So you can see how that's super helpful. You can kind of see what pilots are experiencing. They can make a report to ATC, and then we get a better idea of what the weather's looking like. So I started reading through a few. This is how you read it. There's two types of PIREPs. There's urgent and routine. So urgent for like tornadoes, extreme turbulence, icing, hail, low-level wind shear, ash. Routine doesn't contain like urgent information. So when we read it, the first type is the type of PIREP. If it's normal, it's a UA. If it's an urgent PIREP, right, routine is UA. Urgent PIREP is UUA. Then the location, so over whatever the location is, the time, the altitude, and then the aircraft type. So if I see a 737 at an altitude that I'm going to be flying at, and they're experiencing moderate turbulence, and my little Cessna 172, what's moderate turbulence for a 737 is going to be extreme turbulence for me. So that's why it's important to look at the type of aircraft. I've also looked at these before, and I'm like, what is that? What is a, let's just take this, what is this BE-20? So I just kind of like look it up, BE-20, and then I'll see, oh, it's a Beechcraft Super King Air. And so, honestly, it's kind of fun to look at PIREPs sometimes, and I'm just like, what is that? And I realize some people are flying some pretty cool aircraft. And then it'll give at least one element to describe the element. Anyway, you can talk to Flight Service Station if you'd like to report a PIREP. Flying instrument, a lot of times controllers will ask you for conditions, and they'll make the PIREP for you after they ask you. A lot of times I've been asked, it's been about mainly turbulence, sky condition, visibility is what they really want to know, and icing. So again, using Flight Service Station, we can talk to them to receive an in-flight briefing, to give a PIREP. Flight Service Station is there to help you. If we have ADS-B or FISB for our onboard weather equipment, if you've got a Sentry and you fly with that, and that can give you that, satellite weather information, serious weather, or traffic data from our ADS-B. Amazing satellite weather. Be proficient in any installed weather equipment that we have on the Cessna 172 Sierras, the G1000s. We have NexRad, and that can give us some information, but that information can sometimes be 15 to 20 minutes old. And so that's why it's important we don't just use the NexRad data on our avionics to circumnavigate things like thunderstorms, because we can get old data and we can think we're well outside of a thunderstorm when in fact we're right in the center of it. So when we make a go, no-go decision, consider weather, aircraft equipment, as well as yourself. So we do a weather briefing. So everything we talked about, all the things we went through, I'm going to go through. So what I like to do if I'm doing a weather briefing, I'll start big and then zoom in. So I'll look at the weather chart. So if I'm looking at this, I know that we're going to get a lot of precipitation. The weather's getting worse. I've got a strong pressure gradient, so we've got high winds. So anytime soon, I'm not going to be flying. If I'm up in here, most likely. This doesn't give me that full picture, though. And then I can look at things like the TAF, SIGMETs, AirMets. Looks like we've got strong surface winds coming in with this pressure system that's been moving in off the coast. Then I'll go through, and I'm going to go through all of these, ceiling visibility, clouds, precip, thunderstorm, temperature, winds, turbulence, icing. I'm going to go through all of that in my weather brief. Center weather advisory, seeing if there's anything within the next 2 hours if I was using center weather advisory and I'm flying soon. This may be more something that you check right before the flight. Another one that I kind of like is these forecast discussions. So I can go to that and click, and it kind of breaks it down into plain English. So light rain spreading inland today with a warm front. Flow aloft is north-northwest. Low end VFR this morning and afternoon, trending down to minimum VFR tonight as trailing cold front moves inland like we saw on that prognostic chart. The Seattle depiction forecast discussion, the SeaTac one rather. Light rain today, lowering back to minimum VFR tonight. Southeasterly winds 4 to 8 knots. So with minimum VFR, maybe you're not doing a big long cross country unless conditions are way better somewhere else. But this kind of breaks that down into plain English. We're going to use our weather briefing charts and resources and reports. PAVE checklist, go through the PAVE checklist and your I'm Safe checklist. Consider our overall recent flight experience. We'll go through, it's a good idea to go through a FRAT tool to make sure you're making good, competent go, no-go decisions. Setting personal minimums and not bending them. A lot of times, students starting out, they don't know what personal minimums to set. How you can start to develop personal minimums is before you go fly and, you hear the ATIS and you hear, okay, well, it's 3,000 foot ceilings today. Like, look outside and think, okay, 3,000 foot ceiling, that's what that looks like. Be in the air, be like, this is what it's like to be in a 3,000 foot ceiling, or this is what it's like to fly in 7 miles of visibility. And it's a lot less, I remember, than I thought it was going to be, because you always hear, even when you're flying in 10 statute miles of visibility, I always associated 10 statute miles with unlimited visibility, where you've got 60 miles of visibility. But when you actually fly into 10 miles of visibility, you realize there's a whole lot less that you can see than when you just hear 10 miles visibility on a clear day on the ATIS, because that's just the maximum that it says. Consider your flight experience. You could be current, but more importantly, are you proficient? Are you able to competently carry out the demands of the flight that you're going to potentially take to a high degree of competency and skill? That's the question you have to ask yourself. Recognize weather hazards. Interpret aviation charts, reports, and route updates and in-flight reports. Continual process of decision-making, flight planning, and route. If I'm in the middle of a cross-country, I'm not going to be afraid to discontinue or divert if all of a sudden I encounter adverse conditions. Potential go, no-go decisions. If I have potentially reduced visibility, hazardous weather, there's a PIREP that makes me reconsider. Someone saying that there's crazy turbulence or they're picking up icing, if it busts your personal minimums. Usually if I'm about to go flying and I'm in doubt whether I should go or not, err on the side of caution. You'd rather be on the ground wishing you're in the sky rather than being in the sky wishing you're on the ground. That's what my old instructor used to say. That was pretty much it. We talked about really the importance of the go, no-go decision. There was a lot of information there regarding weather theory and weather information and all the different advisories and weather charts. And, reading the PIREPs, TAFs, METARs is almost like decoding a a different language sort of, but once you get used to it, you practice reading them, it becomes a lot easier. If you go on to ForeFlight, SkyVector, aviationweather.gov, go to a random METAR and try to read what it is. And if you see something that you don't know, what if I zoom out and we're going to go right here and just read a random station. Looks like Fort Scott Municipal, 15th day past the month, 21:55 Zulu, automated weather observation, wind 360 at 12 knots, gusting 16, 10 statute miles of visibility, overcast 1,900 feet, temperature 2, dew point -1, altimeter 2981. Remark, AO2 means an automatic precipitation discriminator, so it can tell if there's ice pellets, rain, snow. And then that T is giving us more precise dew point temperature data. So it looks like a positive 2.2, and then the 1 is a negative for 0.08 dew point. So there you go. I don't know. Go to areas where there's bad weather and try to read that. Here's one. Look at that. On the METAR, that's on the top line. The TAF is following. We have SN, which is snow. FZFG, freezing fog. We have VV011, vertical visibility, 1,100 feet. Temperature -6, dew point -7, altimeter 3013. Automatically discriminating precipitation, sea level pressure. There you go. That'll help you start to pick up on the different acronyms or like decoded icons or little phrases in the METARs. Anyway, that's it for weather. That was a lot of information. This is one where you really can't fully know every single thing after one time being exposed to this information. It takes a lot of time to get comfortable with the weather theory and weather information, and over time it just becomes integral to checking the weather and making safe go-no-go decisions, which is ultimately why we learn about all this. Anyway, that's about it.